Good morning, dear students. In this presentation, we are going to see about electrochemical workstation, its components, working principle, applications, and modes of operations of electrochemical workstation. Electrochemical workstations are vital instruments which are used in modern research. These devices allow precise control and measurement of electrical parameters like current, voltage, impedance, and the mechanisms occurring at the electrode-electrolyte interface. And we can define the electrochemical workstation as its core. It consists of a potentiostat and a galvanostat which control and monitor electrochemical reactions. These systems typically work with a 3-electrode setup that includes a working electrode, a reference electrode, and a counter electrode. By controlling the potential or current, the workstation facilitates the investigation of processes such as redox reactions, corrosion, and energy storage mechanisms. The electrochemical workstation consists of basically an electrochemical cell where we have 3 electrodes: working electrode, reference electrode, and counter electrode. And this electrochemical cell can act as a potentiostat or a galvanostat. This electrochemical cell is also interfaced with the computer. With the computer, we can analyze the data. So let us now see how the electrochemical cell is acting as a potentiostat or the galvanostat. Potentiostat and galvanostat are the heart of electrochemical workstations, and these instruments are responsible for controlling the electrical parameters during the experiments, and we can analyze both the applied signals and the measured responses. So here the potentiostat, first let us see the potentiostat, and potentiostat is used to control the potential difference between the working electrode and the reference electrode. So it maintains a constant voltage or scans through a range of voltages which allows researchers to study how a system responds to different electrochemical conditions. So by controlling the potentiostat can drive oxidation or reduction reactions at the working electrode, which are fundamental to the understanding of electrochemical processes. The potentiostat continuously monitors the current flowing between the working electrode and the counter electrode. This current is a direct measure of electrochemical reactions that are taking place, providing insights into the kinetics and mechanisms of the processes under study. In contrast to the potentiostat, the galvanostat controls the current flowing between the working electrode and the counter electrode. So in potentiostat, voltage is maintained between the working electrode and the counter electrode. But here in galvanostat, the current is flowing between the working electrode and counter electrode. By holding the current constant, the galvanostat allows to study how the system's potential evolves over time under a constant current. This mode of operation is especially useful when investigating the electrochemical reactions that are current dependent, such as that is used in corrosion or electroplating processes. So the potentiostat or galvanostat provides us with a versatile range of control options, enabling the study of various electrochemical phenomena. The ability to either fix the potential and measure the current in potentiostat or fix the current and measure the potential as in galvanostat makes these instruments powerful tools for analyzing electrochemical systems. As we have already seen, The electrochemical workstation consists of the basic element which is electrochemical cell. And the electrochemical cell houses the electrolyte solution. And the electrolytic solution is poured into the electrochemical cell and the electrodes are immersed into the electrolytic solutions. And the most common setup is three electrode system. One is working electrode, the second one counter electrode, and the third one is the reference electrode. On the electrochemical workstation, most of the recent ones are interfaced with the computer where we can get the data, analyze the data and interpret the data, and all these are possible with the modern electrochemical workstation. Let us now see about these three different electrodes in detail. Working electrode. The working electrode is where the electrochemical reaction of interest occurs. Materials commonly used for working electrodes include platinum, glassy carbon, gold and various modified surfaces depending on the specific reaction being studied. The electrode material is chosen based on its conductivity, stability and inertness in the specific electrochemical environment. Reference electrode. The reference electrode serves as a stable and known reference point for the potential applied to the working electrode. The most common reference electrodes are the saturated calomel electrode and the silver-silver chloride electrode. The potential of the reference electrode remains constant, allowing the potentiostat to accurately control the potential of the working electrode. Counter electrode. The counter electrode often made of inert materials like platinum or graphite completes the circuit by allowing current to flow through the electrochemical cell. Its role is to balance current coming from the working electrode, but it does not participate in the electrochemical reactions directly. Thus, the three electrode setup ensures that the system can control the applied potential while accurately measuring the resulting current, leading to more precise and reproducible experimental results. In the modern electrochemical workstations, we have a sophisticated control software that manages experiment protocols, collect data, and provides tools for analysis. So the features are it can be customizable and real-time data can be visualized and we can analyze the data, plotting graphs with them and all the interpretation can be directly taken from the graphs, and therefore this software is essential for simplifying the workflow in electrochemical research. Principle of operation of an electrochemical workstation. The operation of an electrochemical workstation is based on the principle of electrochemical reaction. So what is an electrochemical reaction? It is a chemical process and that is accompanied by the flow of electrons. So electric, flow of electrons, electric as well as the chemical process is taking place. By precisely controlling either the potential or the current, we can analyze or we can probe various aspects of these electrochemical reactions such as kinetics, mechanisms and the efficiency. The basic principle involved in operation of electrochemical workstations are oxidation that is taking place at the anode and reduction that is taking place at the cathode. Let us see this in detail. So the main core of the electrochemical workstation is the study of electrochemical reaction. And these electrochemical reactions involve the transfer of electrons between an electrode and a species in the electrolyte. These reactions can either be oxidation or reduction and they occur at the interface between the working electrode and the electrolyte solution. What is an oxidation reaction? Oxidation takes place at the working electrode, which is anode, where a chemical species loses electrons. For example, in a simple metal ion experiment, a metal atom may lose electrons and dissolve into electrolyte solutions as metal ions. M metal atom now becomes Mn plus N into E minus, that is metal ions and electrons. It loses electrons at the anode. At the anode interface, then reduction occurs at the cathode working electrode in some setups, where a chemical species gains electrons from the electrode surface. For instance, metal ion in solution may gain electrons and deposit as a solid metal on the electrode surface. So Mn plus N electrons E minus becomes M. This is the reduction reaction. The basic law involved in this redox reactions are Faraday's law of electrolysis. The current I measured during an electrochemical reaction is directly proportional to the rate of the reactions as described by Faraday's law of electrolysis. I current I equal to N into F into A into R, where I is the current and N is the number of electrons transferred per molecule of reactant, and F is the Faraday's constant, which is 96,485 coulomb per mole, and A is the surface area of the electrode. R is the rate of electrochemical reactions. The electrochemical workstation also consists of electrochemical impedance spectroscopy. It is a main tool for those researchers working in the field of electrochemistry, and it's a powerful technique for studying the impedance, that is resistance of an alternating current of electrochemical systems. So what is the principle involved in the electrochemical impedance spectroscopy? EIS. EIS involves applying a small alternating current across the electrochemical cell and measuring the system's response over a wide range of frequencies. That's from hertz to million hertz. By analyzing how the system's impedance changes with frequency, researchers can study various processes including charge transfer resistance, diffusion and double layer capacitance. So impedance, we know it's a complex quantity, which is Z is equal to Z prime plus JZ double prime, where Z prime is a real part which is resistant and Z double prime which is an imaginary part, and we can call that as a reactance. Reactance may be reactance of a capacitor or reactance of an inductor. The main feature of the electrochemical workstation is it can act in different modes of operation. The modes include cyclic voltammetry, chronoamperometry, chronopotentiometry, and electrochemical impedance spectroscopy. So, understanding these modes and their functions is essential for choosing the right experimental setup based on the desired experimental investigation. Cyclic voltammetry is one of the most widely used technique in electrochemical research. It involves applying a linear sweep of potential to the working electrode and then reversing the direction of the sweep after a set of potential is reached. This results in a cycle. This results in a cyclic change in potential over time, allowing researchers to probe both oxidation and reduction reactions in the system. The principle is, in CV, the potential is varied linearly with time, starting from an initial potential, sweeping to a predetermined limit, then reversing back to the starting potential. The current response is measured as the potential is changed. and it provides valuable information about the redox behavior of the species under investigation. So the graph that is plotted is known as cyclic voltiogram, and it plots the current I versus the applied potential E. A typical CV plot is shown here, and it has peaks for oxidation and peak for reduction. So oxidation peak, when the potential reaches a point where oxidation occurs, a peak appears in the current response, indicating that the species of the electrode surface is losing electrons. Similarly, a reduction peak occurs during the reverse peak. A reduction peak is observed, indicating that the species is gaining electrons. And the key parameters of the CV is peak current is proportional to the concentration of electroactive species and the scan rate. The peak potential provides insights into the thermodynamics of the redox reactions. The separation between oxidation and reduction peaks reflects the reversibility of the electrochemical reaction. So the applications of CV is extensively used in the study of redox reactions, charge transfer mechanisms, kinetics, and it is particularly valuable in characterizing new material for energy storage devices such as batteries, supercapacitors, and also it has its applications in sensors. The next mode of operation is chronoamperometry. It is a technique in which a constant potential is applied to the working electrode and the resulting current is measured over time. And in chronoamperometry, the potential is stepped into a new value and the current is recorded as a function of time. And from the current time curve in chronometry can be analyzed using quadral equation, which relates the current to the square root of time. So I is a function of time here, and I of t is equal to NFA d power half CO by pi power half t power half, where I of t is the current at time t, n is the number of electrons transferred, F is Faraday's constant, and A is electrode area, D is diffusion coefficient, and C naught is concentration of species. The chronopotentiometry is a reverse of chronoamperometry, where a constant current is applied and the resulting potential is measured over time. So in chronopotentiometry, the applied current causes the potential at the working electrode to evolve as a function of time. The key insights are the shape of the potential time curve provides insights into the kinetics of the reactions and the transport processes involved. For example, a sudden change in potential might indicate the depletion of reactants or the formation of new phase at the electrode surface. Let us now see the data interpretation of cyclic voltammetry. And from the cyclic voltogram, we can get several information or several parameters can be extracted, including peak currents, peak potentials, and peak separations, all of which offer insights into the kinetics and thermodynamics of the reactions. So peak current IP, the magnitude of this peak current is directly related to the concentration of electroactive species and the scan rate and the diffusion coefficient. And for a reversible redox process, the peak current can be described by Randall-Civic equation as IP equal to 2.69 into 10 power 5 n power 3 by 2 a d power half c naught mu power half, where IP is the peak current, n is the number of electrons transferred, a is the electrode surface area, d is the diffusion coefficient, c naught is the concentration of electroactive species, and mu the scan rate. So it depends on the scan rate too. By analyzing the peak current, Researchers can determine key kinetic parameters such as diffusion coefficient and the number of electrons involved in the reactions. So let us now see the applications of electrochemical workstations. First and foremost is in energy storage device. And we know that the energy storage devices like batteries and supercapacitors are now in high demand. That is, more R&D is happening in this area because of high demand for efficient and sustainable energy storage devices. And batteries in the electrochemical workstations are used widely to study electrochemical behavior of materials for lithium ion batteries, solid state batteries, and advanced battery chemistries. And this CV, cyclic voltammetry, and linear sweep voltammetry, electrochemical impedance spectroscopy allow researchers to evaluate charge discharge behavior, life cycle or cyclic life, the capacity and internal resistance of battery materials. And in supercapacitors or ultracapacitors, which are the energy storage devices that store charge for a long time and can also be studied using this electrochemical workstation. And they are playing a key role in the study of supercapacitors. Second application is corrosion. Corrosion is a major challenge for materials in various industries including construction, energy and transportation. Electrochemical techniques are among the most effective tools for studying corrosion. Corrosion rate determination can be studied such as potentiodynamic polarization and linear polarization resistant techniques are used to study the corrosion rate. Electrochemical workstation can measure the corrosion rate of materials in different environments. And passivation and inhibitors. Electrochemical workstations are also used to study the behavior of passive films on metals, such as the protective layers on a stainless steel. The effectiveness of corrosion inhibitors is in reducing metal degradation that can be evaluated through techniques like EIS, electrochemical impedance spectroscopy, and chronoamperometry. Third application is sensors and biosensors. Electrochemical sensors and biosensors have become indispensable in the field of healthcare, environmental monitoring, food safety, etc. So, electrochemical workstations are critical for the development and characterization of these devices. First, let us see the glucose sensor, where it is mainly used to monitor the blood sugar level in diabetic patients, and workstations are used to study the electron transfer rate, kinetics and sensitivity of the electrodes that detect glucose through enzymatic reactions. So in environmental monitoring also, we can use electrochemical sensors that detect contaminants such as heavy metals, nitrates, and pesticides in water and soil. By employing techniques such as square wave voltammetry or differential pulse voltammetry, workstations help in achieving highly sensitive and selective detection of these contaminants. Biosensors. In the field of biosensing, workstations help in the development of sensors for detecting DNA, proteins, and pathogens. Techniques such as electrochemical impedance spectroscopy are crucial in studying the binding events between the analyte and the biosensor, leading to the design of more effective diagnostic tools. And the fourth application is material science and nanotechnology. Electrochemical workstations are pivotal in exploring new materials and new nanostructures for various applications, ranging from catalysis to electronic devices. The ability to characterize materials electrochemically allows researchers to fine-tune their properties, or that we can tailor the property of the material by characterizing it with the electrochemical workstation. Like catalyst. In the development of electrocatalyst for fuel cells, electrochemical techniques like linear sweep voltammetry and chronopotentiometry are used to assess the activity and stability of the catalyst. For example, the oxygen reduction reaction and hydrogen evolution reaction can be studied to improve catalyst for renewable energy technologies. Dear students, in this presentation, we have seen what is an electrochemical workstation, what are the components of electrochemical workstation, and how this electrochemical workstation can operate in a different modes such as amperometry, chronopotentiometry, and electrochemical impedance spectroscopy, etc. And using electrochemical workstation, what are all the various data that can be obtained and how we can interpret the voltogram, cyclic voltogram, all these we have seen. And finally, we have seen the various applications of electrochemical workstation. And I think it is useful for your higher studies or research in the field of material science and nanotechnology. Thank you.